In this lecture, we'll learn about how you can use the math models as a mathematical abstraction for your implementation. Let's first of all see the learning objectives for this particular lecture. So we will hope that you will know how to create a mathematical abstraction for alternative implementation. So when you got multiple implementations that you have to choose from, and then you should really have a common contracts to write them. And the best way to choose will be some mathematical abstraction. That's something we'll see by using a running example. So number two, we want to introduce to you two design principles, namely information hiding versus single choice principle. So these two are very important for you to judge whether your design is appropriate or not. Number three, we want to review some basic of your discrete math, maybe from EECS3311. So this will be self-guided study. I'll give you one example, and then you should really go over the slides to see if you got any questions. And your quiz will actually cover this particular self-guided study. Okay, let's see a motivating problem here. Again, we are reviewing the stack example, but before we do that, let's see what complete contract really means. That's from your last week's lecture about how you can write complete postcondition. Okay, I'm just going to go through very quickly. So recall what we did about complete contracts. So we say to write a postcondition, you should really relate to pre and post states. And then you want to use the O keyword to really refer to the pre-state, and so that you can memorize the pre-state values and then compare them against the post-state. And then also, especially when you got composite structure, attribute array, linked list, or hash table, etc. Especially we did an example for array. You have to say what the intended change should be there, for example, to change index I. But you want to make sure the rest of the data structure, maybe from index 1 to I minus 1, and also from I plus 1 until the end of the array, should remain unchanged. So that's what we said in the previous lecture. Okay, so now let's revisit this particular technique by specifying a LIFO stack, last in, first out stack. Especially we're going to consider a realistic scenario. So when you're implementing a particular data structure, there might exist multiple implementation strategies for you to choose. Let's enumerate at least 3 strategies over here. So let's see this table here. So we're going to list all the features that we're going to implement for the stack, and then we'll talk about 3 strategies. Strategy number 1 is about how you can implement using an array, and strategy 2 and 3 will be about how you can implement a stack using a linked list. Especially, well, for the count, it will be easy. You can simply call, and then we'll call the implementation attributes imp. Okay. The size of the stack will be very easy. We just simply call imp.count. It's the same between array and linked list. But what's really going to distinguish between these 3 will be how do you treat the top of the stack. Okay, so let me just tell you the idea over here, and now visualize it. In the case of the array implementation strategy number 1, so now try to make sure you understand when I say strategy 1, 2 versus 3, you know which one I'm talking about. For strategy number 1, so the last element of the array will be the top of the stack. And for implementation strategy number 2, the first element in the stack, so the first element in the list will be the top of the stack. And strategy number 3 is a little bit similar to strategy number 1. So the last item in the list will be the top of the stack. Of course, between 1 and 3 is about array versus linked list. So let's take a look at some visualization over here. So we got 3 strategies, and strategy number 1 uses an array. The other 2 use a linked list. So let's say we are considering this particular stack, and then the top of the stack is simply just Tom, and the next top will be Mark, and then Alan. So for strategy number 1, the end of the array will be the top of the stack. So that's why we got this order, Alan, Mark, and Tom. So Alan, Mark, and Tom. So Tom is simply the top. And for strategy number 2 over here is kind of like a reverse. So the front of the list, the first element of the list will be the top of the stack. So it's Tom, Mark, and Alan. So Tom, Mark, and Alan. So you can see it's exactly the reverse order as opposed to strategy number 1. For strategy number 3, we are also using a linked list. But now you can think about the order of storing the stack contents will be similar to strategy number 1. So you can see Alan, Mark, and Tom. Alan, Mark, and Tom. So it's just that this is a linked structure as opposed to just indexing structure over here. So now you can see the top of the stack is actually going to be Tom. So it's Alan, Mark, and Tom. So Alan, Mark, and Tom, right? So you can see the order over here. Apparently, you can see order-wise, 1 and 3 are the same. But if you say structure-wise, 2 and 3, they are the same. Okay, just want to show you that realistically, you might just have multiple implementation strategies for you to choose from. But now the question would be, what kind of contracts you can write in order to ensure your supplier's obligation will always be fulfilled, and also its complete contracts. Let me just go back to our table over here. So now you know very well the difference between the three strategies. So now just make sure you remember whenever I say strategy 1, 2, or 3, which one I'm referring to. Okay, so now we also can do push, and push would be very easy. Push to the end of the array using force. And also, if you want to, for strategy number 2, you simply insert to the first of the list. Okay, there's some command you can use from the linked list class over there. Okay, you can also say implementation.extend for strategy number 3. It's quite obvious. And then when you say pop, basically you want to retrieve some element from the array. In that, let's say you can just remove the tail over here, just at the end of the array. And if you want to remove the top, so you will actually first of all go to the start of the list, and then versus go to if you talk about strategy number 3, you will go to the end of the list, and then you can just remove it, right? So you can also just go to LIFO Studio and then look up the specific features about the cursor operation, so you will see exactly why we're doing this. We also made the source code available to you. You should also take a look to actually see how they work. Okay, so now this is the critical question to actually continue with our lecture. Given that all the strategies 1, 2, and 3 are meant for implementing the same ADT, last in, first out stack, will they have identical contracts? Namely precondition, postcondition class invariants. But to make it simple for this lecture here, we only worry about pre and postcondition. Maybe you want to consider specifically for postcondition. Before we move on with the lecture, you should really pause the video and think about how would you write the postcondition for, let's say, push. Would you write it identically between strategy 1, 2, and 3? Would you? Think about it. All right, so let's see. Let's talk about strategy number 1. So very similar as before, so I don't need to repeat. We got an array implementation here for the stack, and then we just create empty stack in the beginning, and also we want to make sure the count for the implementation in the beginning is simply just 0. It's initialized to be 0. So now about the push. Okay, so for the push, let's say we have no precondition. You could introduce one precondition by saying maybe the capacity of the stack should be limited to maybe 100 or 1000, but it's up to you, your design choice. Let's just say we have no limited, it's unlimited size of stack. So we will simply enforce to the end of the array, and now we want to do actually two things, right? We want to talk about what's changed and what's not changed. So now we want to talk about the two implementation strategy, the 3. But let's say strategy number 1. According to strategy number 1, we know that we're actually going to push to the end of the array over here, right? That's what we're going to do. So now how do we write a post condition? For example, let's say over here, for strategy number 1, let me use blue. If I simply say, let's say simply a stack, right? Or just say S, okay, the stack, dot push. Let's say we simply say gym. And over here, the stack might be implemented using either strategy 1, 2, or 3. Okay, let's talk about strategy 1 only. If we want to do this, what's going to happen here, right? So let me help you a little bit, and then you can also specify that. Let's imagine that this is the pre-states over here. That's before, okay? We already got 3 elements in the stack. And in the post states, after this, let me just draw 2 separate stacks just to show you. But you should really imagine that at the runtime, there's only 1 stack. So after this, what we're going to get is we're going to get still an array, but now we're going to get 4 elements inside, right? We're going to get Alan, and also we got Mark, and also we got Tom. And the new elements we have just added will be Jim. Okay, so these are the 4, right? So now how can we write a post condition? Well, for the first one here, it's about what's changed. Well, what's changed? The top will be changed, right? So now you want to say basically, for example, the last elements over here should be Jim. Agree? Okay, so now what indices will be 1, 2, 3, and 4. So 4 is exactly the count of the stack in the post states. So we can say the following. Okay, you can always pause the video before you see the answer. Okay, So now, so for the change, we'll simply say implementation at position count would be G. Okay, so now you can think about if this is the implementation array, right? The implementation array over here in the pre-state and the post-state. How do you compare? So this is the implementation in the post-states over here. So now we want to say implementation account will be 4. At position 4, it should be referring to Jim. Okay, that one's easy. What about the second one? The second one, what about unchanged? You want to actually specify that everything else stay the same. Before I give you some visual hints, why don't you think about it? You might need some quantifier, logical quantifier to help you. Okay, let me give you a visual hints. In terms of this particular scenario, after insert Jim, we know that this is new element. That's been specified already by the first post condition. So now what about the second post condition? We want to say if you compare the pre and post states, you want to say basically Alan over here is the same as the Alan over here. Mark over here is the same as Mark over here. Tom over here is the same as the Tom over here, right? So now, more precisely, index 1 should be correspond to index 1. Index 2 should be corresponding to index 2. Index 3 should also be corresponding to index 3. So that's a simple case, actually. But how would you write it? So let me just write in the universal quantification quickly in math. And then you have to translate it into LIFO, which you will see in the slides. So remember, the post condition will be checked at the post states, in which case count will just be 4 rather than 3, right? It's been grown already. So we would say for every, and for the notation I'm going to write, it's been covered already in the introductory tutorial and also in the Q&A session. So you can check them out if you're wondering about the notation. For every I, such that the lower indices, assuming presumably will be 1. Okay, we can make that assumption. Less than or equal to I, less than or equal to. So now we only worry about only the old contents basically, right? So 1 should be 1, 2 should be 2, and 3 should be 3. So the only item we want to exclude will be the new top basically, right? So now how do we specify that? Well, we can say simply imp dot count minus 1. That's what we can say. So we are excluding this particular index to look at. It is the case over here. So now we can say, how do we refer to the pre-states? Well, we learned about in the previous lecture, you can use deep twin to really prevent from any aliasing effects to actually affect our reasoning for the post condition. So we can say imp dot deep twin. And then at position I, so now we are lucky because position 1 will be corresponding to position 1, 2 will be corresponding to 2. So we'll simply say tell that equal, because we talk about string value, for example, in this case. It will be the same as, we simply say imp at position I. Okay, so that's about strategy number 1, post condition for that particular one. I'm writing this down because I want to contrast with how we will write it for another strategy. For example, strategy number 2. We'll get there in a moment. But make sure you're comfortable with this. And how would you translate this into LIFO? That should be quite straightforward. Okay, let's go back to the slides. And that's exactly what you will have, okay, over here. Okay, I'm going to leave that to you. I already showed you the derivation process for this. And similarly, if you want to do the pop, in which case we remove from the end of the array. In that case, how would you do the changed? Well, the change would be, since the element would not be there anymore. So, and also the size of the stack will be shrunk. In that case, we would say, for example, count would be equal to O count plus minus 1. Okay, that one's easy. So what about unchanged? So I want you to follow the same visualization over here, if that helps. So now think about how you will write the unchanged post condition here. For that one, I'm not going to go in detail. I'll leave that to you. Okay, it should be very similar to the derivation process as this one here. Okay, I'll leave that to you. Okay, it's going to be this. Verify that you believe it is correct. Right? In the quizzes, I might just modify that a little bit to really ask you if that will still be valid. Okay, so you really want to make sure you understand this. Let's now talk about strategy number 2. Specifically, I want to talk about that particular post condition we just did to see changing your strategy wouldn't necessarily change the contracts. It may or it may not. So that's something we got to worry about. Okay, so now we still got the implementation here, but it's a linked list right now. And we do strategy number 2, which means the first item of the list is the top, as we went over before. Okay, we still got the constructor here. We got the push, And then, so now the change will be similar. We just say, watch, it's similar, but it's the opposite. So we say the first item in the list will be equal to G. You can already see this post condition here is already different from the corresponding one in strategy number 1. Because in strategy number 1, we say imp at position count will be equal to G, right? So you can see somehow changing the strategy of implementation affect the way you write a post condition, which is revealed to the public, to your clients. So you really want the interface to remain as stable as possible. If you only change your implementation internally, why would you have to bother your clients who actually have already understood your previous contract? So that's really a flaw of your design. So now, what about unchanged? So now let's think about, before I show you the answer, how we can think of it correspondingly. Okay, so now let me use the same stack over here, and we're still talking about as the push will be equal to, we want to push Jim. So let's say, let me use a different color in this case. Why don't I use maybe green over here? Okay, so as the push Jim. Again, we talk about pre-states and we talk about post-states. Let's say this is the pre-states, and of course, let's say this is the imp over here. What about the post-states? The post-state is going to be, because we want to treat, in strategy number 2, we treat the first element of the list as the top of the stack. So what we'll do is, let me just draw that. Eventually, we'll get 4 nodes over here. Let me draw that quickly for you. 1, 2, 3, and also 4 over here. Of course, this is pointing to just void. And then, so this will be the new imp in the post states. And where will Tom, Mark, and Alan be? Over here, right? Because you can think about it's more like shifted to the right, visually speaking, right? So now this will be Tom, so this will be Mark, and this will be Alan. And then the new one, Jim, will just be here. So Jim will be the new top over here. You can think about at the same time, this is the top of the stack. So now we know that the first post condition will say the top of the stack will simply just equal to the front of the list. That's been done already. So now we want to know how we can say the rest of the stack stay the same. So we want to say the Tom here is equal to the Tom here, Mark here is equal to the Mark here, Alan here is equal to the Alan here. However, what about indices? Index 1 should be equal to index 2 in the post states. Index 2 in the pre-state should be equal to index 3 in the post states. Index 3 in the pre-state should be equal to index 4 in the post-state, right? You can see like a one-off relationship over here. But how do we specify that in a similar way? Okay, let me write it down over here. So now for number 2, which will be strategy number 2, that will be green. So in a similar pattern, but it wouldn't be identical, would it? So let's say for every I, so we say, so now we simply want, how do we quantify over? Well, in this case, you can see we don't worry about this particular top anymore. So it should be starting from 2 and then 3 and then 4, right? So now the range will be different already. So you want to say from 2 less than or equal to I, less than or equal to imp dot count. It's basically saying we're going to go from 2, 3, all the way until 4, the last one. And then it is the case over here. So now how do we say? Okay, so now let me just put down something here and then we can fill in the blanks. Imp.deep twin. I just noticed that from the previous one, I forgot to actually put the O keyword over here. Maybe you have noticed that. Okay, sorry about that. So now also here, we should also refer to the pre-state. So we're gonna say the O keyword here. And then let me put just put this blank just for now. It will be equal to imp at position something. Okay, so now this is basically, this is the pre-states. And this is the post states, right? So this is the post states over here, and this is the pre-state over here. So now how do we tell the difference, right? You can see if the pre-states is simply, for the post states, if this is I, what should that be? Well, this should be I minus 1, right? Because for example, this is index 2, that should correspond to index 1. Index 3 should correspond to index 2. Index 4 should correspond to index 3. I'm just moving a little bit fast because it's quite basic math. But if you really got a little bit of trouble, please slow down the video and try to rewatch. Okay, so that means I, and then that'll be corresponding to I minus 1. So I will put I here, over here, and then this will be I minus 1. You got to be careful with about the indices you put. Okay, so that will be the second post condition. Yeah, just again, please make sure you remember to put O keyword, which I forgot in the previous one. Okay, so now let's take a look. So that's exactly what I just said. So you can see this is I in the post states, and then be I minus 1 in the pre-state. But here I'm just using the S rather than is, but you will see what I mean over here, right, for the across notation. Okay, so now also similarly, you should also try to do an exercise on the pop over here, okay, just to see why it should be exactly over here using this cross notation here. Again, for this particular version, I'm using S, so that means you got to say I the item as opposed to just I. You have to know the difference from the introductory tutorial video. Okay, so we still got number 3 for strategy. Number 3 we haven't discussed that, but very similar. So I'm going to leave that to you to see how the contract should be written. Okay, so now the main lesson for you to learn from so far is we got 3 different strategies for implementing the LIFO stack. That depending on which strategy we choose, we have to define their contracts accordingly, which means whatever we publish to the clients has to be changed if the internal implementation changes, which is not a good thing. Okay, you want to make it like that. If the internal implementation is changed, it shouldn't affect the client's understanding about the contracts. That's something you want to keep in mind, and that will be related to the 2 design principles we're going to talk about in just a moment. So I'm going to leave that to you for strategy number 3. Okay, got to convince yourself it's really correct over here. Okay, if you got any trouble, speak to me. So now let's introduce the 2 design principles over here at one go. One is about information hiding, and the other one is about single choice principle. Information hiding is very important. It's really about whenever you got any supplier's design decision that are likely to change, you better hide them. So what are the design decision here for the supplier? Well, internally, should you use a linked list or should you use an array structure-wise, right? Number 1. Number 2, if you use a linked list, should you treat the first element of the list being the top, or should you treat the last element of the list to be the top? So there are at least 2 design decisions you have to make. So that's a design decision. But should the clients be bothered by that? No, absolutely not. So violation of information hiding means that your design's public API is unstable. So let me, I'll demonstrate that to you in just a moment. Okay, and also when you change the supplier secrets, you should not affect the clients relying upon your existing API. Let's say if the client is already getting very used to strategy number 1 for your contracts, if you change to strategy number 2 and suddenly you change the contracts, the client will be shocked, right? So now what about single choice principle? So the idea would be, it would be very nice if we can have just the same contracts for all the 3 possible implementation strategies. So the supplier can freely change from one to another internally, and the clients will always understand the identical contracts. It's definitely not the case right now. And another design principle is called single choice principle. That's single choice principle basically say there's no duplicates, because if there are duplicates, every time you want to do updates on the duplicates, you can update multiple places because you got multiple duplicates. So when a change is needed, there should be a single place, meaning that there's no duplicates where you need to make that change. I'm gonna illustrate to you also in the code. We'll see many examples about single choice principle in this course. So this is the first one. And then violation of single choice principle means that you contain redundancies or duplicates in your design. Okay, so now we want to see how our stack example actually violates these 2 design principles. Let me demonstrate that to you also on iPad. Let's just go over slides and then we'll get there. So the post condition of all the 3 strategies, they're complete because we talk about what's changed and what's not changed. As far as that is concerned, we are being consistent with the previous lecture. But now we have other concern about information hiding versus single choice principle. That's a new concern. So you can see now over here, why does it violate information hiding? Let's see this. So changing the secret internal workings of data structure should not affect any existing client. But how does that violate this information hiding principle? So let's say this. The implementation over here is actually referenced in the post condition. However, we are basically making public the following detail. For example, the top of the stack, it could be, according to strategy number 1, the end of the array, or strategy number 2, the first element of the list, or strategy number 3, the last element of the list. This will actually make all their contracts different. Let me show you right away. So now, just say for example, so this will be strategy number 1. So let's take a look. For strategy number 1, let's say for the push, right? So this will be basically the top of the stack, which is the last element of the array. For strategy number 2, it will be imp.first. For strategy number 3, it will be imp.last. You can see all the 3 strategies are actually specifying for this particular post condition. So these post conditions are completely different. So the clients can only understand these 3 post conditions if they understand your implementation strategy. But are the clients supposed to understand your implementation strategy? The answer is no. So there's one design flaw because you expose the implementation secret, like using either array or linked list, and also the order of the contents to your clients, to the public. So that is a no-no. Okay, so that's about the violation for information hiding, and also you can see also about how you write other parts of the post condition. For example, let me just give you another one. Over here, you can see this part here, you're just going over from 1 to count -1. And over here, you're doing from 2 to count, right? Again, it's different. And this one is 1 to count -1. And over here, you can see you got I.item -1, and also I.item, right? The client shouldn't be bothered so much by such subtleties, right? But now we are forcing them to understand such details because we are referring to imp over here in the public contracts, which should not be the case. Okay, let's talk about also why we also violate. Okay, so this is really why we are violating the information hiding. Changing the implementation strategy will also change the contract, which is not good. And we also violate single choice principle. Easy to see. Why? Because imagine this. Let's say this. If I simply modify, let's say from strategy number 1 over here, if I change from strategy number 1 to strategy number 2, what do I need to modify? I need to modify multiple places. Place number 1, I need to modify this, right? From here to over here, place number 1. And also place number 2 from here to over here, right? Post condition are completely different. And also for place number 3 here to over here. Place number 4 here to here. It's basically all over the place. I'm changing all the contract just because I switch from an array into a linked list with the reverse order. So that's violates single choice principle. It should be a single place, like a single routine or single class, but not single class, a single routine where you actually try to do all the changes, which will be the case if we use a math model. We'll see how that's going to happen. Okay, so now up to now we talk about the 2 design principles that I want you to learn, and you want to really make sure you understand why the current existing design, which use 3 possible strategies of implementation, will actually violate these 2 design principles.